is actually from it's from a different course, but there's a formula for this, so I just need to go find it.
Sure.
So let me just do that. Are you seeing my screen?
I am.
Okay.
Just of the, I think you're in OneNote or something. I'm just seeing the problem.
Yeah. Okay. I couldn't tell if I had shared or not. It was unclear. Okay, so the part A here, the formula is the square root of 2 times the demand times the ordering cost all over the storage cost. And this actually is this is in this is usually taught in a different course, but it nevertheless is here. So we have 894 is our demand, 894. The reorder cost is $8. The storage cost is 3. And oh, this actually does work out because it says round to the nearest whole number. So let's see here if we got the numbers in right. 894. Okay, oh, it says type a whole number. Don't like that because it didn't work out nicely. The example I'm looking at is also not nice, so we'll just assume that it rounds here to this ends up being 69.051. So let's go with 69 for A.
Cool.
I have a better answer than that. Now the reorder is another formula, so I got to grab that. All right, so the reorder quantity for B is N, but this is Q, by the way. This formula is for Q. It's N over Q. So it's the annual demand, which in this case is 894 over the 69.051, and we will round that to the nearest decimal place and get 12.9. That is it for question 1. The next, let me just look through this so I can see what to expect. Okay. Yeah, okay. We will, this will go faster. They just sort of threw the first couple are the more difficult ones in this unit. So let's move on to question number 2. Following demand function is given, and you have to determine all of these things. So the demand function is given here, and you want to determine elasticity of demand. Elasticity of demand is minus P over Q times dq dp. Would like to verify that. That's a straightforward one here. So we have to find a couple of things here. They want a formula here for it, but we'll get to that in a moment. So let me just confirm that that is the elasticity of demand formula. Right. Okay, yeah, that looks good. So P is your variable. So in terms of this, you're going to keep the minus P, your Q is given, and then you have to take a derivative of this thing right here. So that's using power rule. The derivative of the first one is 0 minus 6P. And so you really need three things. So your expression for elasticity demand is minus P divided by 36,200 minus 3P squared times minus 6P. So this is what goes in that first box there. We can clean it up a little bit if you want here. It becomes minus 6P, I'm sorry, positive 6P squared. Let me actually remove that in the numerator over 36,200 minus 3P squared. So that's everything for that first box there. Okay, now to do part B, there's actually a couple ways to do it. One is to set the elasticity of demand equal to 1. That's something you would learn in an econ class, which you're not in. The other is to look at the revenue function. Revenue is price times quantity, and you already have your quantity function that's up here. So you take your price, multiply it by 36,200 minus 3P squared, which is your quantity. And I like to go and graph that. I like to graph that and just find the max there. So that's what I will do. I'm going to go to the other screen and graph that because it's easier than doing some calculus, setting equals 0. And I'm using X instead of P when I graph. All right, so the most challenging part of this is to just get the right window. I'm using Desmos to do that. Okay. There it is. All right, let me snip this in so you can see what it looks like. Wow, it's really large. The revenues are really high in this problem. That's why I'm sort of just taking it back a little bit here. So, all right, so it says this is that graph that I mentioned that I was graphing here. So this right here would be your P, which we don't want. It wants Q. Q is the output. Now, you are not asked for revenue, even though it says total revenue is maximized. You're asked for the Q. So you use this P value, the 63.421, and you plug it into the quantity for the expression for quantity. So your quantity expression is 36,200 minus 3P squared. We're going to use that 63.421. And whatever that is, that's the Q that we want. So I got to go back to another calculator. This is a fairly complicated problem to like be the first one you've ever seen of this type. So I would certainly understand if it wasn't as clear as it could be. 21 squared format. Okay, so this is round to the nearest whole number, 24,133, and that's this box right here. Okay, and that's it for that question. We'll move on to question 3. All right. So again, they're giving you a quantity function up here. They're telling you that Q is this function right here, and it's a function of P. P is your variable, and this problem though is more numerical. So your elasticity of demand formula, sometimes use uppercase E or lowercase e. I've never really gotten enough clarity on that, but it's this formula right here, minus P over Q times dQ dP. So this time they give you the P. They tell you P is 97. So that's minus 97 over your Q is taking this 97 and plugging it in for P in the F of P equation up here. So it's kind of messy. Not P, it's 97 to the power of minus 0.04 times. And so you're taking the derivative of this and then you're evaluating it at 97. So there's kind of a lot going on here. I'm kind of doing it all in one step. So the derivative is minus 0.04 times that 1563850 times p to the minus 1.04 power. That's the power rule. But again, you're evaluating that at 97. So what I tell students is to evaluate them all separately, rather than trying to do everything at once, because it is kind of a lot here. So price is 97, and then Q is when you plug that 97 into the f of p up here. So let me just
Hey,
get that.
Matthew,
Yes.
just a quick question. I lost you when you got that negative 1.04.
Yes, you're just subtracting 1 from the exponent power rule.
Okay, thanks. Thank you.
That's it. Like it looks weird. It is weird. I mean, I don't even know how they could come up with this, but they did. And yeah, you just go with it.
Okay.
1563850 times p. Okay, so then so just to be clear here, p is 97. Q, when I plug p into this up here, and you're welcome to try that with me, it's this number 2339.5, a bunch of other things. And then the last one we need is the derivative at that point, and then we'll combine all three, the dq, dp, and get that here. So times minus 0.04 times that. And that is minus 537.04723, blah, blah, blah. So now what I'm doing in the calculator is I'm combining the P and the Q and the dq dp, but I'm letting the calculator do all of it, like assigning variables, and then you just read your answer out, get your answer out of that. So that, believe it or not, it works out really nice. It ends up being 0.04. But wait a second here. Why is it asking? Why is it asking for it twice? It's really weird. Let me check this problem online, because it's asked for the elasticity demand point. That's what we just calculated. But this says what is the elasticity demand for oil when the price is? Feels like it's the same question.
Yeah, I agree.
But I don't understand. So let me go check. It's almost like that's mistyped. Like they meant to say the demand for oil is, but I can't be sure of this. Look at another reference here.
Should I like email my
No, I
professor?
mean, no, I think this is just one of those where it's just we got to just figure out what they want.
Mhm.
Not seeing anything here that's helpful. I guess just because we don't have a ton of There might be a problem like this in the homework that would have helped, but I guess I would just tell you to put the same number in both places and not worry too much about it. And then this last question, it depends on this value to get the answer. So I gotta remember where is, so there's these ranges. So if it's like from 0 to 1, 0 to 1 means something, and then greater than 1 means something else, whether it be elastic or inelastic. So just need to look those up because I don't do this very often where I have to remember this.
Okay.
Demand value. Okay, so if it's greater than 1, it's considered elastic. And if it's less than 1, it's considered inelastic. And so that will help us to answer this because we're between 0 and 1. And what that means on the curve, by the way, this is actually more important part. The inelastic region is to the left, is your inelastic region, and your elastic region is to the right. And you really want to be at the top. So if it's inelastic, that means you're like somewhere over here on the curve, which means you need to charge more so you can get to that max revenue point. So, and if you're elastic, you're charging too much, you need to charge less to get back to that max revenue point. So that it looks like letter A would be correct on that one, because you want to increase your price to increase your revenue because you're not quite at the top there. Hopefully that's the last of these. Yeah, goodness, boy, what a nightmare.
I know, I'm not seeing like the relevancy here.
Yeah, if we had real data, we would have, you know, some fun here, but there's too many things going on to try to explain it. So now we're moving to just a completely different topic altogether. It's called implicit differentiation. And it looks kind of the same as what we did in like maybe chapter, you know, a couple units ago. So the ones that you can do for sure without issue is like, what's the derivative of 5x squared? And that's 10x, okay? And but from here, you got some problems. So we're going to come back to the 9xy for a moment. The derivative of 7y squared, you use the power rule. So it's 14y, but whenever you take a derivative with respect to y now, you add a dy dx. Okay, so it's like a little bit different, a little bit of a wrinkle. So now when you look at 19y, the derivative of 19, if it was 19x, it would be 19. But whenever you see a y, it's now dy dx. And the derivative of -5 is 0. Okay, so the only thing we're not sure how to deal with is this 9xy. And this one's really frustrating for students. So it's product rule. And the derivative, I'm going to show you the answer. The derivative is 9x dy dx, okay? And that's keeping the first being this 9x, derivative of y is dy dx. Then you take the derivative of the first, which is 9, and keep the y. And this is terribly confusing. We don't really have the time to like jump into all the reasons here for it. So this is your setup. And then from here, you're just solving for dy dx. Okay, so to do that, you move any non-dy dx terms to the other side of the equation. So that what that does, that means remove the minus 10x over and the minus 14y over. A lot of writing on these, by the way. And so you're left with 9x dy dx plus 14. Nope, I'm sorry. We cannot move the 14y. That's tied to the dy dx. You can see that. So plus 14y dy dx plus 19 dy dx equals minus 10x. And then you factor out the dy dx. That's in every one of these. So it's 9x plus 14y plus 19. And then you divide that to the other side of the equation. So dy dx equals minus 10x over 9x plus 14y plus 19. And that is your implicit derivative. Now let me check that because it's very easy to make a sign error in these, and don't really want us to have to redo any of these problems today. So let me just grab this. I need to scroll up slightly. Sorry if you're typing that in. I'll scroll back down a moment. My caps lock on. Okay, XY. All right, so I did miss something here, didn't I? Oh, that 9y. That's what I was meant to move. Okay, sorry. There's a 9y in the numerator. I didn't catch that. So there's this minus 9y is what you move to both sides. Yeah, this is good. This is good now. So this is not a good example for us to start with for like the first time you ever learn this, but we'll the next one will be slightly better. I'm gonna just move on here. All right. So if you just look at this part on the left here that I'm boxing in, and you just do the implicit derivative like we talked about, the derivative of x squared is 2x. Okay, no big deal. For y, what you do with y is you treat it like it's an x, so it would be 2y is your derivative. But whenever you take a derivative with respect to y, you have to add in this dy dx. The derivative of 29 is 0. And then you solve for dy dx. This one's a little bit more straightforward. You subtract the 2x from both sides. I'm going to just come down here and you get 2y dy dx equals minus 2x. And then you divide by 2y. So you got dy dx equals minus x over y. But that is not the answer. You have to now plug in your x and your y, because what you want is a slope. If you recall, when the derivative is the slope, you get the slope from the derivative. So you plug that x and y value into the derivative. We previously only put in the x value, but that's the slope right there, minus 2/5. All right, so now your equation of the tangent line, I like going y minus y1 equals your slope, x minus x1. This is point slope form. So you use the x and the y that you're given, but they're now x1 and y1. So it's y plus 5 equals minus 2/5 x plus 2. Now, in terms of what you enter into this box up here on the right, it's solved for y, so you have to also solve for y. So it's minus 2/5 parentheses x plus 2 minus 5, and that's your final answer for that one. Oh, wow, another implicit derivative. Okay. All right, so question, I think we're up to 6 here. So it says find the equation of the tangent line at the given value of x. Basically the same problem. The implicit derivative is a little bit harder here than the previous one. So again, like when you have a y, you treat it like an x. You're like, all right, it's really 3x cubed. That's power rule. That's 9x squared. I'm sorry, 9y squared. You still have to write the y. But then if you, with respect to y, there's a dy dx. Okay. And then the middle one, this xy, that's the one that's most problematic. It's really chain rule. So it's u v prime plus v u prime, but it gets confusing because it's x and y's. So the shortcut here is it's x dy dx plus y. And then this minus y, the derivative of it was just minus 1x, it would be minus 1, but you have a dy dx whenever you have a y there. And this equals 4 times 192, which is 800 minus 32, 768, 768 x cubed. So just like the previous problems, you want to solve for dy dx. So you move the non-dy dx terms to the side. So just the y there. So it's 9y squared dy dx plus x dy dx minus dy dx equals 768 x cubed over, sorry, not over. We're subtracting the y. We're subtracting the y from both sides. Then you factor out the dy dx. So 9y squared plus x minus 1, there's really a 1 there. 768x cubed minus y over 9y squared plus x minus 1. Let's see that those cancel. Okay, but that's not what they want. They don't want the derivative. They want the tangent line, which means you have to plug in x and y. Problem is you don't have y, which is kind of frustrating. So to get y, you have to graph this and then figure out where the y value is. I mean, or you could use like a guess and check approach. So I'm going to graph this and snip that in. All right. Okay. Wow, that's really horrible. 3y cubed plus xy minus y equals 192x to the fourth. X equals 1. Get this snipped in. Why don't they intersect? All right. Grabbing a snip now. You ever seen on social media where they make like Valentine's Day? They probably do some stuff for Halloween with like curves. This is like when you have variables and when you have x and y, you can do more things with your curves. So this is why this one's so weird. But when x is 1, y is 4. Okay. And you're just finding the intersection of those two. So we need that point because we need to evaluate the derivative when x is 1 and y is 4. So I'm going to go to my calculator. I'm going to say x is 1, y is 4, and I'm going to evaluate the derivative here. And I'm really hoping it works out nicely. I should also check it with another calculator just to make sure we've got it. And that didn't work out great. Okay, let me check the implicit derivative of this. It's so easy to make an error doing these by hand. Okay, yeah, this is correct. So it doesn't work out nicely. Let me get the fraction. Wow. Okay, so this ends up being when you plug in your x and your y, 191 over 36. And so your equation of your line is y minus y1 equals your slope x minus x1, and your x1, I'm sorry, your y1 is 4, your slope is 191 over 36, x minus 1. So the last thing I can do just to check this, and actually let me move this 4 over, add 4 to both sides, is I'm going to graph it and just visually inspect, like, does it actually look like a tangent at that point? Because it's supposed to visually look like that. So let's do that. 1 over 36, x minus 1 is 4. So I'll snip that in so you can see that. And you've heard, maybe you've heard before the phrase sanity check. And that's what we're doing here. We're like, well, like kind of looks tangent, although you could argue, well, you haven't zoomed in enough, but yeah, it looks pretty good to me. I would assume that's reasonable. So this, just to be clear, this is what they're looking for in that box there. All right. Oh boy, more of these. These are just never ending. Okay. Okay, find d squared y over dx squared by its implicit differentiation. This one's more difficult because you got to take a second derivative, but you start by taking first derivative just like we've been doing. So the 11x squared is 22x. The second one is 18y dy dx equals 0. Right. Now, normally you solve this for dy dx, and we do need to do that. But before we do that, we're actually going to take a second derivative. So with respect to x, that's just the same thing, 22 power of that. This one, 18y dy dx, this gets really confusing. You're now using product rule with derivatives. So you keep the first, take the derivative of the second, that's d squared y dx squared, plus the derivative of the first, which is now 18 dy dx times the second dy dx equals 0. And what's usually unclear for students here is that you're just squaring the derivative over here. It's just dy dx times itself equals 0. So you need that, and you get that from this first line up here. So we have to go and solve this for dy dx. You have to kind of do that off to the side here. So I'll do that, and then we'll continue with this path over here. So you're going to subtract 22x and divide by 18. So dy dx equals minus 22x over 18y. It is worth simplifying here, minus 11x over 9y. That is your dy dx. That is what is going to go into this formula for dy dx squared. So it's 22 plus 18y d squared y over dx squared plus 18 times minus 11x over 9y squared. There's no calculus at this point. At this point, it's all algebra, essentially. 121x squared. So 9 squared is 81, but you've got that 18 out in front that we should deal with. Why am I struggling with this? Let me go to the calculator to get that 18. Yeah, so that ends up being, well, we'll do that in a moment. 18 times 81y squared equals 0. 22 plus 18y d squared y over dx squared. And you might be wondering, like, where are we going with all this? Well, you're solving for d squared y. And yeah, it's bad. It's really bad. So to get that, this, let me get this right here. So we got 18 times 121 over 81. All right, so on the right here, this becomes 242 over 9x squared y squared, but we're going to move that to the other side of the equation. So we're subtracting it, and then we're going to subtract this 22. Okay, and so you're left with this 18y d squared y over dx squared. So you divide both sides by 18y like this. And then it's a question of, well, how much simplifying do you need to do to get it into the right answer? So let me manipulate this a little bit. 18. So this becomes minus 121 over 81 y cubed x squared. And then, minus 11 over 9y, like that. So this should be correct. I'm going to check it as well because reasonable that I would have made a mistake amid all those. So let's go second derivative of. So on a paper exam, they don't give you very many of these to do because they take a lot of time. Let's go derivative. Didn't like that at all. Okay. Yeah, this is my best shot for that one. Okay, we're moving on to. Not sure. I guess this is 8. Keep going here.
This is 8. I sent it to you in like 2 parts.
Yeah. Oh, it's nice. We actually don't have to calculate it. I see. Oh, okay. Oh, you have to calculate it. Never mind. That we got away with one. Okay, so you can think of when we were doing x squared plus y squared equals 1500 kind of problems like this, y is really a function of x. Okay, so when you're doing dq dp like this, and this is all really awkward because it's the variables are all switched around, but you're doing so p is usually x and q is usually y, so they're really asking for dy dx. So y, it's really like saying y is a function of x, and so in your problem it'd be q is a function of p. If you assume that q is a function with respect to q, boy, I really think it's the second one. Boy, these are horrible. Yeah, let me just check here. Two p squared plus q squared. Differentiate with respect to q. No, we're differentiating with respect to p. That's what it is. Okay. With respect to p, okay, you just have to read these again. And assume that q is a function of p. Okay, this one is correct because we are differentiating with respect to p. The variable on the bottom is the with respect to, so it's either c or d. And we're assuming that q, that doesn't seem right. dy dx, dy is sort of different to x. And then q is a function of p. Yeah, that's right. Okay. Wow, that's really horrible. Okay, yeah, that's what we got here. Okay, so now as far as how to proceed here, we're just gonna go straightforward here, just like we've been doing. Assume that p is really x, so it's 4p plus 2q dq dp equals 0, and then you solve for dq dp, and then So your dq dp ends up equaling minus 4p over 2q, which is minus 2p over q. So this is your correct answer. Which one does it go in? It's the rate of change of demand with respect to price. So it goes in this top one. And then I think we do the same thing, but we switch. We're just switching the order there. Yeah, let me grab this one so that it's very clear. So essentially just a flip of what we just done here. So we're differentiating now with respect to Q. So it's either B or C with respect to Q. And now P is a function of Q. That should be the reverse of the one we just did. Yeah. P is now a function of Q. So it looks like letter B is correct. So the weirdness of this is that now it's 4P dP dQ plus 2Q equals 0. And you're solving for dP dQ. dP dQ ends up being minus 2Q over 4P. So minus Q over 2P, minus Q over 2P. And it goes in the other box here. It's price with respect to demand. So it's the top box. It's just the flip of this one. And this is either all completely right or all completely wrong, because I either, completely missed it or didn't get it here.
Made sense to me, but
Yeah.
it doesn't say much.
These are just really confusing. And it gets, so calculus 3 is where you start doing a lot more of this. And it's just very confusing because it's very much like everything's nested inside of these other things.
Yeah, no, this seems like actually horrible.
Yeah, I would, yeah, well, we can say it for another time. All right. So assume X and Y are functions of T, evaluate dy, dt for the following. So this one, it appears bad. It's actually way better than the first one. So you just take your derivative like we've always done. So y cubed becomes 3y squared, but you go dy dt, throw that in there. And then same thing with x, it's going to be 6x squared dx dt. But notice they give you dx dt. Okay, so and they give you a bunch of other things here. So your dy dt, if you're solving for that, it's 6x squared dx dt over 3y squared. And you have all these numbers. It's 6 times 1 squared times 4, that's dx dt, over 3 times 2 squared, because y is 2. And this one, by comparison, is very, very, very tame and nice. And I don't know why they can't be like that, but let me just check this one. So it ends up being just 2. Let me just check this one more time. 6x squared dx dt, 3y squared. Yep. Y equals 2, dx equals 4. Yeah. Okay. So the answer is just 2. You can go 2.00 if you want, but it's just 2. Okay, there's more. Let's keep going here to 10.
The drop down is increasing or decreasing.
Yeah, that makes sense because it's asking about the rate of change. So they're asking about the derivative. They're encoding in this that dx dt is 13, and they're also saying that x is 60. So it's dc dt, this implicit derivative, 0.8x dx dt, derivative of 8,000 is 0. So you're just plugging in these numbers like this. Your x is 60, dx dt is 13. and we'll just get a number out for that. These aren't actually relatively, they're much easier. So 624, that's this number here. Because it's positive, it's increasing. All right, we're moving on to 11. I was reading that the superstition associated with ladders actually is more to do with paint falling on people and tools, not bad luck. Or that the bad luck is that happened.
That you hit it right
Yeah,
and it
yeah.
falls. Oh,
Yeah,
that's interesting.
yeah. That's so. Anyway, nothing to do with this question here. So it's an 8-foot ladder leaning against a building. So this is your triangle problem. So we're saying, all right, here's an 8-foot ladder leaning against a building, and the bottom of the ladder is sliding along the pavement directly away from the building at 3 feet per second. So this is your X prime. And they want to know how fast the top of the ladder is sliding down when the foot of the ladder is 3 feet from the wall. So basically when Y is 3, they want to know how fast it's sliding down. So to do this, you use the Pythagorean theorem. And I'm choosing X to be the base, Y is the height, and D to be the hypotenuse, not A, B, and C. So you're doing these implicit derivatives. So it's 2x dx dt plus 2y dy dt equals 2d dd dt. And the ladder itself is not changing in size as it goes down. So this whole thing is 0 because the ladder itself doesn't change size. It's always 8. So then we solve for dy dt. dy dt equals minus 2x dx dt over 2y. And then you can just do a small cancellation, minus x dx dt over y, like this. Actually, yeah, we'll do that way. That's fine. So you need x, y, and then dx dt. So the x is the only thing we don't know. This is x right here, and you get that from the Pythagorean theorem. You get from x squared plus 3 squared equals 8 squared. So you get that x squared equals 64 minus 9 square rooted. So x is the square root of 55. And so that goes into your formula here, minus square root 55. Dx dt is 3, and your y is 3. Wow, look at that, they cancel. But you do have to put that into the calculator and get a final number, minus square root 55. So it says thousands, right? So that's minus 7.416. But very important here, we know it's already negative because it's sliding down. So we don't have to actually put that negative in. It's just 7.146. It's already accounted for in this problem. Let's cancel. 3 feet. Okay. All right. Last one here for today. Rock is thrown into a pond. Okay. All right, a rock is thrown into a still pond. The circular ripples move outward from the point of impact of the rock so that the radius of the circle formed by the ripple increases. So the radius is increasing. That's r prime of 3 feet per minute. Find the rate at which the area is changing. So area of a circle is pi r squared. And that's all we have to go off.
I really don't like this past coming to haunt me either.
You throwing rocks into ponds?
Well, no, it's the Pythagorean theorem and then this area of a circle, and I just hate it.
So the calculus students, they always ask, they say, do I have to know these formulas for the test, or are you going to give them to me? And the instructor's always telling them, hey, you're supposed to know these from a previous class.
Great.
Yeah, I don't know. The formula is not really, I mean, it's crucial to doing it, but it's not part of the calculus. So you could sit there and have the argument. You could say, well, are we testing them on their knowledge of this formula or the use of calculus? Because then, but then you could argue, well, why not make it a more sophisticated formula then? If we're going to give them the formula, these are all, you know, not related to anything we're doing, but these are questions I would ask, you know, people.
Right.
You know, what are we testing here?
Right.
And the other thing is this question is completely online. I mean, you could find, it may not have the exact same numbers, but you can sort of plug in some of the same, you know, and probably get it right.
Mhm.
So the derivative here, a prime is 2 pi r prime. And you have all the numbers now, 2 pi times 9 times 3. And they want you to round to the nearest thousandth. So you just go right to your calculator and get a number. 2 times pi times 27. 9 times 3 is 27. And you get 169.646 as your final answer.
All right. Okay, well, I'm gonna submit it. We'll see what
Yeah,
happens, I guess.
hopefully things are okay on this one.
Let's see. Oh yeah, no, that's good. 87.5%, and I got 1.5 wrong.
Okay.
Yeah,
So
no, that's good.
There's all right. Well, I guess that's it for today. I guess just keep going here. Got a few more weeks probably until the final.
Yeah, yep, a couple more, and then yep, we're seeing the light at the end of the tunnel for sure.
All right. Well, thank you so much for scheduling, and I'll see you notes here shortly, and I'll see you next time.
Sounds good. Have a good one.
Okay.
Bye.
Bye.